This slide presentation will examine all three types of regression that are covered on the AP Statistics exam. Hopefully, you have been introduced to all three, and this presentation will serve as a review of the important aspects of each. To make the presentation more interesting, slides will alternate between important terms and methods and an example that illustrates these methods. Bivariate Data examines the relationship between two variables. There are several questions you must answer when you analyze bivariate data as shown on the slide. We will be interested in relationships between quantitative variables in this slide presentation. When determining which is the explanatory variable and which is the response variable, you must think about which variable explains the other. For instance, if we are examining the relationship between how much time a student studied and his grade in an exam, it makes sense to say that time is the explanatory variable and grade is the response variable. The reason is that we would like to say that your grade is explained by how much you study. There are times when it is difficult to determine this explanatory-response relationship. For instance, if you were looking at the relationship between someone's height and their shoe size, you would have to ask whether height explains shoe size or shoe size explains height. If you cannot answer the question, then it makes no difference which is the explanatory variable. A diver is investigating a wreck in the ocean and has come to the surface. On the slide is a table that describes his depth in feet from the time he starts ascending. Since he is below the surface of the water, we will use negative numbers to describe depth. Answering our 5 basic questions. The data describes the diver. There are 2 variables, time and depth. For convenience, it is easier to convert time to seconds and depth is measured in feet. It makes sense to say that depth can be explained by time, so depth is the response variable and time is the explanatory variable. A scatter plot is a graph that shows the relationship between the explanatory variable on the x-axis and the response variable on the y-axis. Each axis of scatter plots must be labeled and have a uniform scale. In this scatter plot, the time variable has been converted to seconds. You can create scatter plots on your calculator. When interpreting a scatter plot, you need to be concerned with 4 pieces of information. Form. Your eye will tell you whether the dots appear to be in a line, in a curve, or in clusters. Direction, also called association. Positive associations go up to the right. Low values of the explanatory variable accompany low values of the response variable, and high values of the explanatory variable accompany high values of the response variable. Negative associations go down to the right. Low values of the explanatory variable accompany high values of the response variable, and high values of the explanatory variable accompany low values of the response variable. Strength of the association. We are concerned with how closely the points follow a form. Usually, we are only concerned with strength when examining linear associations. The first scatter plot shows a positive linear association that is fairly strong. Your eye tells you that the points are fairly close to being along a line. The second scatter plot is a negative association going down to the right, and your eye tells you that the association is curved. The third scatter plot is a clustered association. There are 4 points on the lower left, and then 5 points on the upper right. The fourth aspect of a scatter plot is deviation from the form. This usually occurs when the data have outliers. An outlier is a data point that falls outside the overall pattern of the relationship. There are tests for outliers, but usually an outlier sticks out like a sore thumb when viewing the scatter plot. On the left scatter plot, the point 12, 4 is an outlier. Your eye tells you that that point clearly falls outside the linear pattern. But on the right scatter plot, the point 35, 72 is not an outlier. If the line were drawn through the points on the lower left, it would come close to passing through the red point. So when we look at the scatter plot of our diver, we can make the following observations. Our eye tells us that the association is linear, and it is certainly positive going up to the right. The association is fairly strong, certainly not a perfect association when the dots would line up along a straight line. There appears to be an outlier, shown in red, as all the dots go up, signaling the diver is rising, and then there is a dot that goes down. When asked after he gets to the surface, the diver said that he dropped something along the way and went back down to retrieve it. For that reason, you decide to eliminate the outlier. To measure the strength of the association, we find that our eyes are not a good judge. You might think that the lower scatter plot has a stronger association than the top one, but they are both our diver data, shown in different scales, so their associations are the same. We use the variable r to represent the strength of the association. To r, we use the formula. r equals 1 divided by n minus 1 times the summation of the product of x sub I minus x bar all over s sub x times y sub I minus y bar over s sub y, where n is the number of data points, x bar is the mean of x, s sub x is the standard deviation of x, y bar is the mean of y, s sub y is the standard deviation of y. For each point, x sub I, y sub I, you calculate the product shown and add them up. Finally, divide by n minus 1. Thankfully, you do not need to know this formula on the AP exam, as you will either be given the value or your calculator will determine it. You just need to know how r is used. Facts about r. r is greater than or equal to -1 and less than or equal to 1. Positive values of r indicate a positive association, and negative values of r indicate a negative association. Values of r near 1 or -1 mean a very strong association. Values near 0 mean a very weak association. It makes no difference which variable is explanatory when calculating r. r doesn't change when the units of measurement of x and y change. r only measures the strength of linear associations, not curves associations. r is non-resistant. It is strongly affected by outliers. The least squares regression line is a straight line that describes how the response variable y changes as the explanatory variable x changes. The least squares regression line is the line that makes the sum of the squares of the vertical distances from the line for each data point as small as possible. As you run the video on the slide, notice how, as the line is moved to various locations, the squares change, and so does the sum of the squares of the line. We want the one special line that makes this sum a minimum. Your calculator will calculate the least square regression line. As shown by the slide, its formula is depth hat equals 0.292 time minus 227. The hat means that it is a predictive formula. We can predict the depth using this function of time. Many software packages will give you the value of r squared when calculating the least squares regression line. We know that r is the square root of r squared. Since we know this is a positive association, r will be positive. The fact that r being 0.985 and so close to 1 tells us that the association is very strong. There are certain facts about the least squares regression line that you need to know. First, the form of the line is y hat equals a plus bx. All least squares regression lines go through the point x bar, y bar. There are formulas for slope b and y-intercept a. Slope b equals r times the quantity s sub y divided by s sub x, and the y-intercept is given by y bar minus b times x bar. You do not need to memorize them, as they are on your formula list given to you at the start of the AP exam, but you do need to know that these formulas exist. It is important to understand the interpretation of slope b. For every unit increase in x, the predicted y variable changes by b units. Finally, we have the coefficient of determination, r squared. Not to be confused with r R squared is the percentage of variation in y that can be explained by the least squares regression line. If, for instance, you are measuring the relationship to the amount of studying one does compared to the grades in a test, and you get R equals 0.9, strong positive association, then R squared equals 0.81. You say that 81% of the variation in grades in the test can be explained by the least squares regression line of study time on grades. That means that 19% of the variation in grades can be explained by other factors other than study time. Let's do linear regression with our diver data. With our least squares regression line formula as depth hat equals 0.292 time minus 227, we find that this line passes through the point 180, negative 174.3, which is the point representing the average of the x values and average of the y values. Since the slope of the least squares regression line is 0.292, we interpret the slope as for every increase of 1 second, our depth goes up by 0.292 feet. This means that for every second, he goes up by 0.292 feet. Since R squared equals 0.97, we say that 97% of the variation in depth can be explained by the least squares regression line of time versus depth. At t equals 4 minutes, we predict the diver will be at 157 feet. Since the value of t equals 240 is within the set of given data points and r is close to 1, we are very comfortable making this prediction. However, at 9 minutes, we predict that the diver will be at depth 43 feet, but our confidence in this prediction is low because the value of t equals 630 is far outside the set of data points. This is called extrapolation, which can be quite dangerous. For example, I might be willing to predict the price of gas tomorrow, but I wouldn't be at all confident predicting it a month from now. The word residual means left over. In statistics, residuals for a particular piece of bivariate data is the difference between the observed response variable y and the predicted value of y based on the least squares regression line. A good way to remember it is observed minus predicted, O minus P in alphabetical order. The first data point in the table is 0, negative 240. The predicted value at time equals 0 is negative 227. Negative 240 minus negative 227 equals negative 13. That is saying that the observed value is 13 below the predicted value. A residual plot is shown. It plots time versus the residual. Points below the x-axis are points where the observed value is below the predicted value, and points above the x-axis are points where observed value is above the predicted value. At time t equals 330, the residual is close to 0, meaning that the observed value and predicted value are just about the same. Most graphing calculators with statistical abilities have a list of residuals that is automatically created when least squares regression is performed. When we have a lot of points, it can be difficult to determine whether data is linear or curved. While there are mathematical tests, which we will show later, a visual way to determine it is to generate the least squares regression line and draw a residual plot. If there is no pattern to the residual plot, it is an indication that the data is best described as a line. If there is a pattern to the residual, that is an indication that the data is curved. In the leftmost example, the data looks like it is linear. When we create a residual plot, we see no pattern to the residuals, so that confirms that the data is best described as a linear association. The eye can fool you. In the right example, the data appears perfectly linear, and when we find the least squared regression line, we find that r equals 1, telling you it is perfectly linear. But when we created a residual plot, we find that there is a pattern to it. That tells you that the original data is best described by a curve and not a line. Looking at the diver data, we examine the residual plot and find that there is no pattern to the residual plot. The conclusion is that the data is a linear association. If the diver surfaces at exactly 8 minutes, we have a new point added to the mix, 480, 0. When examining the scatter plot, we see that, without even doing any calculations, the slope of the least squares regression line will increase. The red point acts like a magnet, increasing the slope. We call this an influential point. Influential points are points that, if removed, would markedly change the slope of the regression line. Typically, points that are outliers in the x direction are often influential. Also, the value of r will decrease. The calculations show that the new regression line in green on the graph now has an r value of 0.94 when it was originally 0.98. Outliers are influential. Influential points are not necessarily outliers. AP Statistics covers 3 types of bivariate data: linear data and 2 types of curved data: data whose regression curve is exponential and data whose regression curve is power. Each has a different equation associated with it. The least square regression line has the familiar equation y equals a plus bx. Exponential curves are in the form y equals a times b raised to the x power. Power curves are in the form y equals a times x raised to the b power. It can be difficult to determine the form that best describes the data by eye, so we introduce procedures to tell the difference. On your calculator, you can perform exponential growth and power growth by pushing buttons. But on the AP exam, you need to understand the process of transformations that have been built into the calculator. In the case of perfect linear growth, the difference of the y values is the same over the same interval. The example on the left shows that situation. When we subtract each y value from the previous y value, we get a constant 6. This signals linear growth. But on the example on the right, we see that the increase from y value to y value is not constant, it is growing. However, if we take the ratio of any y term and the previous y term, we get constant 1.5. This signals exponential growth. When we look at the graph of the data at the top of the slide, we see that it looks linear. We find the regression line and find that r equals 1. However, when we do an arithmetic analysis, we see that the increase from term to term is not constant, but increasing. This tells you that the data is curved, despite what your eyes tell you. This is confirmed by the residual plot, which shows a pattern. When we look at the percent change from term to term, the ratio of each y term to the previous y term, we see that they are the same. This tells you that we have exponential growth. If we take the logarithm of each y term, and then look at the difference from term to term of these logs, we see that we get a constant. This phenomenon always occurs in exponential growth models and will help us to determine the equation. Let's look at the procedure where the growth isn't exactly perfect, which is typical in the real world. We have a new set of data. We plot x versus y and see that it is clearly not linear. When we look at the ratio of the y term to its previous y term, we see that they are not the same, but somewhat the same. That tells us that we should attempt exponential procedures. We are transforming the y variable by taking the log of the y values. We then plot the x versus the log y values. Notice that it appears somewhat linear. That is confirmed by the residual plot that shows no pattern. We create the least square regression line of x versus log y and get log y equals 0.089x plus 0.045. We have a least squares regression formula that is for x versus log y, not x versus y. So our least squared regression line equation is log y hat equals 0.0892x plus 0.045. To solve for y, we take the antilog of each side. We use the properties of powers to break up 10 raised to the 0.0892x plus 0.045 power to 10 raised to the 0.0892x power times 10 raised to the 0.045 power. Finally, we calculate 10 raised to the 0.0892 power and 10 raised to the 0.045 power to get our exponential growth form 1.109 times 1.228 raised to the x power. When we graph this equation, we see that our graph goes through or close to most points in our original data. It isn't perfect, but few situations are. Finally, we can use the formula to predict the y value at x equals 12. We get 13.041. We can also predict the value at x equals 20 and get 67.437, but realize that extrapolation is dangerous, especially when the growth is so fast as happens in exponential models. The example shows data in the form of x versus y. When you plot it, it looks linear. You find the least squares regression line and find that it has an R of 1. However, you know by now that can be misleading, and you examine a residual plot. Sure enough, you notice a pattern to the residuals. So, you check out exponential regression. You compute the log of y and create the least squares regression line for x versus the log of y. However, this does not look linear, and when you create a residual plot, you find a pattern to the residuals. This is an indication that the original data is not exponential as well as not linear. Power growth theory states that if the plot of log x versus log y appears linear, then the graph of x versus y will be a power model. Examining the scatter plot of log x versus log y, it appears linear, and that is confirmed by the residual plot. So we transform the x data as well as the y data. We have a least squares regression formula, but that is for log x versus log y, not x versus y. So our least squares regression line equation is log y hat equals 1.2 log x plus 0.041. To solve for y, we take the analog of each side. We use the properties of powers to break up 10 raised to the 1.2 log x plus 0.041 power into 10 raised to the 1.2 log x power times 10 raised to the 0.041 power. 10 raised to the log x equals x, so our power growth formula is y hat equals 1.099x raised to the 1.2 power. When we plot the least squares regression line and the power regression curve on the same graph, we see that they are very close. However, as x gets larger, we start to see the curves diverge. When we predict the y value at x equals 10, the linear model gives 17.8, while the power model gives 17.4. But when we extrapolate at x equals 40, the linear model gives 76.9, while the power model gives 91.9. Extrapolation is always dangerous, but we always attempt to predict the future based on the data of the past. So it really is important to find the best model for the given data. The procedures for finding regression models for a set of points x, y are given. You should always start with plotting your data. Unless it is clear that the data is curved, you should always begin with linear regression and check your residual plot for patterns. If a pattern exists or the data is obviously curved, you should use the procedure for exponential regression by taking the log of y and finding the regression line for x versus log y and checking for a pattern to the residual plot. If none exists, use the appropriate regression formula. If there is a pattern to the residual plot, use procedures for power growth by finding the regression line for log x versus log y and using the appropriate formula. If there still is a pattern to the regression line for log x versus log y, there are other regression forms that are not covered in the AP exam. If you are forced to choose, use the growth formula whose regression line gives the largest absolute value of R. Let's finish up with a final example. Angelo's Pizza offers pizza in 5 different sizes: cookie, personal, small, medium, and large. The size of the pizza is based on its diameter, and obviously the greater the diameter, the more the cost. Angelo decides to create 2 new pizza sizes, a mini at diameter 8 inches and the Oh My God pizza at diameter 30 inches. Using linear, exponential, and power models, what would be the suggested price, and which model do you think makes the most sense? Since you were asked to do all 3 models, no attempt was made to look at residuals to see which model seems best, and with only 5 data points, it would be difficult to examine patterns anyway. There are only slight differences between the cost of the 8-inch mini pizza in all three models, but huge differences in the cost of the 30-inch Oh My God pizza. From a practical view, the exponential model makes little sense, as no one would pay almost $300 for a pizza the size of a tire. But since the amount of pizza is the area of a pizza, pi r squared, the cost of the pizza should be similar to the area of the pizza, which suggests the power model makes the most sense. We mentioned that the relationship between two variables can be strongly influenced by other variables. Since those other variables are lurking in the background, we call them lurking variables. A study was made in a private school of the relationship between students' age and their height in inches. The scatter plot was shown. Linear regression was done, and we end up with an R of 0.62, indicating fair strength. But when we examine the data further with the lurking variable of gender, we see that our original data was really in two clusters, one for boys, one for girls. If we do linear regression for each, our R values are much stronger at 0.87 and 0.79. One final caution when performing regression. Just because you have a strong correlation between X and Y doesn't mean that X causes Y. For instance, a study examined the total ice cream sales on a popular beach in the summer for a 2-week period, and how many times lifeguards had to rescue people from the water. There was a strong positive linear association between the two variables. However, just because there is a strong association between eating ice cream and lifeguard rescues doesn't mean that eating ice cream causes people to need to be rescued. Ice cream is sold when it is hot, and when it is hot, people swim. Hence, more people need to be rescued. The lurking variable is the number of people on the beach.